Today's lesson will be the first of several lessons about the integral test for infinite series. So in general, the integral test gives you a way to test whether a series converges or diverges by comparing it with a related integral. And in this first lesson, we're going to look at the case where we test if a series converges by comparing with an integral. So the series that we're going to look at is of this form, sum from n equals 1 to infinity f of n, where this f is a decreasing function of x. So a good example to keep in mind is the case where f of x is equal to 1 over x squared. And then our series would be this one here, sum from n equals 1 to infinity, 1 over n squared. Now the idea of the integral test is this inequality. On the left-hand side we have the series, and on the right-hand side we have f of 1 plus the integral of f of x from 1 to infinity. Now you can see that if this integral converges, then the series must also converge because the series is less than f of 1 plus this integral. So that's the main idea of the integral test. And so now we're going to derive this formula. Now the main idea to derive this formula is to study the graph of f of x, which remember is a decreasing function of x. So let me draw this function. So I'm going to draw it twice because we're going to compare the areas of two different regions. So here's f of x as a function of x, and I'm going to draw it between n minus 1 and n, where n is some integer. And you can see that it's decreasing as x increases. Now I'm going to make the same picture again on the right-hand side. Now, on the left-hand side, we're going to look at the total area under the curve between n minus 1 and n. So we're going to look at this blue region here. We can calculate the area of this region using an integral, and it's just equal to the integral from n minus 1 to n of f of x. Now, on the right-hand side, we're going to look at a different region. We're just going to look at a rectangle which touches the curve at x equals n. So its height here is f of n, and it's just a rectangle. So it only touches the curve at f of n. Now we can also calculate the area of this rectangle. It's just equal to the base, which has a length of 1, times the height, which is f of n. So it's just equal to f of n. Now, the key here is that by comparing these pictures, you can clearly see that the rectangle on the right-hand side is smaller than the area under the curve on the left-hand side. So that means that, more formally, we have this inequality. F of n, that's the area of the rectangle, is less than or equal to the area under the curve on the left-hand side, which is this integral. So this is the key formula that will allow us to derive the upper bound for the integral test. So, in just a few lines, we're going to derive that upper bound. We'll start by writing out our series, sum from n equals 1 to infinity, f of n. We'll separate out the first term to get f of 1 plus the sum from n equals 2 to infinity, f of n. Now, we're going to use our inequality on this f of n here. So we'll get that this is less than or equal to f of 1 plus the sum from n equals 2 to infinity of the integral from n minus 1 to n of f of x. Now we have a sum here of these integrals from n minus 1 to n, And we're going to sum up all of those integrals starting from n equals 2 all the way up to infinity. And by looking at all these integrals, you can convince yourself that this sums up to the integral from 1 to infinity of f of x. That's because the first integral here is from 1 to 2, the next one is from 2 to 3, and so on. And we end up summing up all the area under the curve from 1 to infinity. So, putting this all together, we arrive at the final inequality for the integral test. The sum from n equals 1 to infinity, f of n is less than or equal to f of 1 plus the integral from 1 to infinity, f of x. And now you can see that if this integral converges, then so does the series. So let's just write that down. So if the integral on the right converges, then so does the series. And that's the end of this lesson.